Bismillahirrahmanirrahim. In this session, we will discuss the electromagnetic effects. That is a topic from O level and IGCSE physics. In this session, we will discuss electricity and magnetisms are closely linked. Wherever we have electricity, there is a magnetism. Where there is a magnetism, there is also electricity. The effect of producing electricity from magnetism was discovered in 1831 by Faraday and is called electromagnetic induction. And this electromagnetic induction discovery basically led to the construction of the generators which are available in the power houses or power stations, generating stations. So this electromagnetic induction effects was the impetus for the construction of the generators, and as a result the generating stations are developed. Now test yourself, page 231. A magnet is pushed. This is a magnet. N pole first. This N pole is entering first into a coil, as in figure 4.55. Which one of the following statement A to D is not true? The EMF is induced in the coil and cause a current through the sensitive center 0 meters. Yes, true. The EMF will induce because this creates a relative motion here, and as a result this coil or this number of turns will develop an EMF. The induced EMF increases if the magnet is pushed in faster and or the coil has more turns. If the number of turns has increased, or if the these magnets move faster inside this coil, then EMF will increase. Yes, it depends on the speed. So the relative speed increases, then more EMF will induced in the coil. Energy is transferred by electric current. Yes, this magnetic effects creates EMF and electric current will flow here in this coil. The effect produced is called electrostatic induction. No, this is electromagnetic induction. So this statement D is incorrect because this is electromagnetic induction, not electrostatic. This is incorrect because this effect which produce this electricity from the magnetism is called electromagnetic induction. So statement D is incorrect. A straight wire moves vertically upward at a right angle to a magnetic field acting horizontally from right to left. Make a sketch to represent the direction of the magnetic field, the motion of the wire, and induce current in the wire, and if it is connected to a complete circuit. So this kind of sketch we will show in later part. The test yourself, page 223. Which feature of the rotating coil of an AC generator allows the induced EMF to be connected to a fixed contact? This is a rotating coil and it is moving inside a magnet, permanent magnet or an electromagnet, whatever. So this is a magnet where this coil is turning clockwise. So when the coil moves, it cuts the magnetic field lines and EMF is induced. So and this EMF induced at this terminal, this wire is connected to these slip rings, and this slip rings from this carbon brushes, terminal outputs are taken out from here and it may be used in the load. Sketch the output of an AC generator against time. for this generator, EMFs are induced in such a way, because if the coils are in this position, so this coil position is this turning is like this, so this fields and the coils are in the same direction. The fields and coils turning is in the same direction, so when they are in parallel there will be no EMF induced. Here in this position, this coil is moving in this direction, so in this case EMF will be induced 90 degree. So this is A and this is D. This is D. Yes. A is here, D is here. In that case, voltage will be induced maximum. The maximum. When again this is in parallel, so in parallel condition EMF induced will be 0, while in this condition this is moving up and this is going down. So on the negative side this is connected, so we have a negative voltage, highest negative voltage, and afterward this again, this is parallel, so again 0. When this turning force direction and the fields are parallel, no EMF is induced. In this case, and here in this case, no EMF is induced. This is this point, this one and this one. So these 3 points, this point, this point and these points are the where the fields are in parallel. The force is in this direction and the fields are also in this direction, while on the other side the fields and this conductor's movement are in perpendicular to each other, where the fields EMF, maximum EMF, and between these values are these range occur in place from 0 to 90 degrees. This will happen similarly for other cases. So this is the output of an EMF or AC generator against time. This is very, very important. At what position of the coil in an AC generator is the output is maximum? The maximum is here in the above figure. When the coil is turning downward, coil speed is at 90 degree with reference to with respect to the field and cutting the maximum field flux. This magnetic field is cutting maximum linkage is there, which means inducing maximum EMF at this point, because this is going down, this wire is moving this direction and this conductor is moving in this direction. At this position the maximum EMF is induced, and on the other side at this position 0 EMF, because these are in parallel. So at this point when the coil is upright, when the field and coil movements are in parallel, means minimum or no cutting of the field flux, means 0 EMF is induced in the coil for this cases. 0 EMF is induced. Test yourself, page 235. The vertical wire in figure 4.513 is at right angle to the card. In what direction will a plotting compass at A point when there is no current in the wire? When no current in the wire means this compass will show the north position, north direction. The current direction is upward. When the current direction is upward, then this is the downward direction. So in that direction, when we close, the flux direction will show by the right hand gripping rule. So by using a right hand gripping rule, so current direction indicates the thumb position, and the curl of the hand of the right hand will show the magnetic field lines. So when we use a thumb like this, so it's going down, so thumb is pointing downward, so the curl of the right hand will show the clockwise rotation in case of downward current. So in the upward current, this will be reversed. So in the upward direction, the current is going upward, and these fields are moving in the anti-clockwise direction. Anti-clockwise. Here in the downward, it is clockwise. On the upward direction of current, this is anti-clockwise. So this is important. Figure 4.514 shows a solenoid wound on the core of the soft iron. Will the end A be a north pole or a south pole when the current is in the direction shown? So current is in this direction, means the north will be here, because when we close it in the direction, we are curling it, right hand rule. So thumb will points the north here. This is north. So right hand grip rule, according to the right hand grip rule, this will points to the north. So this is north direction. State where the magnetic field is strongest in a current carrying solenoid. In a current carrying solenoid, the field lines are closer together when they are outside. The field lines are closer when they are inside the coil. Closer together. The field lines are closer together when they are inside. This is inside the solenoid, and this indicates that the magnetic field is stronger inside a solenoid than it's outside. So the field lines are closer together inside as compared to the outside solenoid. So inside solenoid will be higher. So this is should be closer together than they are outside. So the field lines are closer inside together than they are outside the solenoid. So inside the fields are stronger, while outside the fields are weaker. Name two factors which affect the strength of the magnetic field around a current carrying solenoid. The number of turns, and the larger current. When the larger current is flowing inside the coil, more magnetic field lines. So the number of turns of the coils, it depends on the number of turns of the coil and the amount of the current passing through the coil. Test yourself. Explain when a relay would be used in a circuit. A relay is a switch used on the principle of electromagnetic. It is used if you want one circuit to control another, especially if the current and power are larger in the second circuit. Here this is a solenoid, and in this solenoid this is the coil. This is a coil. This A and B terminals, at this terminal we supply the current in this to this coil, and this creates a magnetic effects, and this pull this armature, iron armature, which is at this pivot point. As a result of this pulling force here, this will push upward, and as a result this contact will close, and after closing this contact, this circuit will be completed at D and E. As a result of this magnetic circuit here, A and B, this power circuit will complete. Second circuit, this is the first circuit as discussed here, and it creates makes a circuit for the second circuit. So here we have a small current is provided to this coil, and as a result this magnetic effect, this contact will close. It will push here, and as a result it moves up because of this pivot point, and as a result this contact closes and this circuit becomes energized. So this is the way a relay is used in a circuit. The resistance R of a coil in a relay is 300 ohms, and its operating potential difference is 15 volt. So this is resistance is given and the voltage is given. Calculate the pull-on current. So pull-on current is equal to I is equal to V upon R. 15 volt divided by 300 ohms is equal to 0.05 ampere, which is 50 milliampere. The pull-on current in a relay is 60 milliampere and operates at 12 volt. Calculate the resistance of the coil. Pull-on current of the relay is 60 milliampere, which is 0.060 ampere, and voltage is 12 volt. Resistance equal to V upon I. 12 volt divided by 0.060 ampere is equal to 200 ohms. So 200 ohms is the resistance. Explain how an AC signal is converted into sound by a loudspeaker. Loudspeaker basically works on the principle of the electromagnetic induction. When a varying electric current flowing through a coil of wire, this is a coil of wire. When a varying current is flowing through it, or a voice coil, creates a changing magnetic field. It creates a changing magnetic field here. This is a changing magnetic field that interprets with a permanent magnet. This permanent magnet is outside. This changing effect creates a with the varying effect with a permanent magnet, causing the coil to move. This coil to move back and forth like this. Like this. As a result, the attached diaphragm cones vibrates. This cone is outside this cone, which vibrates, and as a result the sound is produced. So this is the way the electrical signal is converted into a audible sound signal by the movement of this cone, vibration of this cone, as a result of the varying magnetic field or changing magnetic field. So this is the electromagnetic induction effect in a loudspeaker, which is the main principle of working it. Test yourself. The current direction in a wire running between north and south poles of a magnet laying horizontally is shown in figure this. The force on the wire due to the magnet is directed from north to south, from south to north, opposite to the current direction, vertically upward. Force on the wire is option D, because it is built vertically upward. If we use a Fleming's left hand rule, because the current is providing to this coil or wire and it is in the magnetic field, so the north to south directions are given here. So this north to south direction is given here, and the current is going inward, so force will be vertically upward. If we use a left hand rule, left hand like this, so the first finger will point the field. This is the field. The first finger will point the field, and the second finger will point the direction of the current, while the third thumb will show upward. The thumb will show upward. So this is that is why that's the force exerts vertically upward. An electron beam follows a circular path in a perpendicular magnetic field. Will the radius of the path increases or decreases if the strength of the magnetic field increases? Why? Here we have electron beam is applied in a magnetic field, and magnetic field is going from north to south inside the page, or inside the page from north to south. This is a magnetic field. This plus sign is showing a magnetic field into the paper, inside the paper, and a beam is, electron beam is applying here. So this electron beam will have exert a force, and a beam of electron that is entering at right angle to the field experience a force due to the motor effect. So according to the Fleming's rule, the field is inside, the current is actually the current, this electron beam is in this direction though, so the current will be in the opposite direction. The conventional current is on the other side. So when the current is on the other side, this force will act downward. So in case the force acting at right angle to the direction of the beam make it follow a circular path as shown. So as a result, this radius will be even lower when a higher beam of current or magnetic field strength is increases. So will the radius of the increase if the strength of the magnetic field increases? As the increase of the magnetic field, as a result of the strength, increase of the magnetic field strength is increases. If the strength of the magnetic field increases, then this force will increase. So it will reduce the radius. Yes, higher magnetic field strength will impart more force on a higher deflection, therefore radius will decrease. So negative beam of charged electron is treated as a positive conventional current in the opposite direction. So the beam of negatively charged electron is treated as being in the opposite direction to the conventional current. If the electron is coming in this direction, then conventional current is going in the opposite direction. So using a Fleming's left hand rule, we can understand, if we put the left hand and point the first finger to the inside the page, the middle finger, the second finger will show on the left side, while the thumb will point in the downward direction. So because of this Fleming's left hand rule, this force will exert downward, and with the increasing magnetic field strength, this force will increase, and as a result this circular path will have a smaller radius, or its radius will decrease because of a more force due to the increased magnetic strength in magnetic field strength. So this will affect. Test yourself, how would the turning effect on a current carrying coil in a magnetic field change if the size of the magnetic field is increased or the direction of the magnetic field is reversed. In a part A, the turning effect on a coil will increase. The turning effect will increase if the number of turns on the coil increases. Coil increases means magnetic field will increase. The current flowing in the coil increases. If the current flowing through the coil increases, then its magnetic field strength again increases. If magnetic field strength increases, the turning effect will increase. If the strength of the magnetic field increases due to any other reason, then again the turning effect will increase. So the number of turns on the coil increases, the current flowing through the coil increases, or any other means the strength of the magnetic field increases, then the turning effect will increase and it will move faster and faster. If the direction of the magnetic field is reversed, then the direction turning effects direction of the force will change. Question number 15. In a simple DC electric motor, figure this 4.5.29, the coil rotating anti-clockwise as seen by the eye from the position X. When current flows in the coil, is the current flowing clockwise or anti-clockwise? Field is moving in the north to south, and the coils and the current is the direction of the magnetic field reverse. The turning effect will follow the Fleming's left hand rule and will turn in the opposite direction. So if current flows or current flowing clockwise or anti-clockwise, so if current is going inside, if it's going inside, then force will be downward. If it's coming out, the force will be upward. So if we change the direction of the current, its force will be changed. See, in case of using a left hand Fleming's rule, using just use your Fleming's left hand rule. So this north to south is the field direction, and if it current is going inside, when current is going inside, the force will be downward. If current is coming outside, the force will be upward. So this is upward and this is downward, means this is anti-clockwise. If the current is coming out from this side and going from this side, then the direction will be clockwise. So this is simple. Just place your left hand and first finger will show the field direction, second finger the current direction, and the thumb will show the force or turning direction. Test yourself. The main function of the step down transformer is to decrease current, decrease voltage, change AC to DC, or change DC to AC. Step down transformer is used for the decrease of voltage. So this part B, because statement B is correct. So step down transformer decrease the voltage from high voltage level to low voltage level, while step up transformer increase the voltage levels from low voltage level to high voltage level. Step up transformers are used in the power stations, and step down transformers are used at the consumers level, at distribution levels. So in our domestic supplies, we get the supply from the step down transformer, from the pole mounted transformers, PMTs. So this B is correct. A transformer has 1000 turns on the primary coil. The voltage applied to the primary coil is 230 volt AC. How many turns are on the secondary coil if the output voltage is 46 volt AC? So we have given a transformer as a primary coil is 1000 turns, and the applied voltage on the primary coil is 230 volt AC. How many turns on the secondary coil if the output voltage is 46 volt? Output voltage is 46 volt, means secondary voltage is lower than the primary. So the number of turns on the secondary will be lower because the voltage on the secondary is lower, 46 volt. So it will be lower than this. So Vp upon Np is equal to Vs upon Ns. Ns is equal to Vs upon Vp into Np. So 46 volt, 230 volt, 100 tons. So result is 200 ton on solution. This answer B is correct, which is 200. 5 times voltage decreases 5 times. So number of turns also decreases 5 times. From 230 to 46 is 5 times decrease. So number of turns also decreases 5 times. Now put this into practice. A transformer stepped down the main supply from 240 volt to 12 volt to operate a doorbell. What is the turns ratio primary to secondary of the transformer winding? So we have 240 volt on the primary side and the secondary side is 12 volt. So on the ratio is 20 to 1. So the number of primary is 20 times more number of turns than the secondary. How many turns on the primary if the secondary has 80 turns? Secondary NS has 80 turns and NP becomes 1600 turns. The primary turns will be 1600 if the primary has 80 turns. So 80 times, 20 times more than the secondary, because secondary has a low voltage, primary has a higher voltage, 240 volt as compared to this 12 volt. So number of primary turns will be 1600 turns. A transformer step up an AC voltage of 240 volt to 960 volt. This is step upping from this voltage to this. Calculate the turn ratio of the transformer winding. So primary voltage is 240 volt, secondary voltage is 960 volt. So number of turns of primary secondary is equal to primary voltage secondary voltage 240 divided by 960. So the number of turns on the primary is 1, then the number of turns on the secondary is 4. If the primary has 500 turns, the primary has 500 turns, the secondary will be higher, 4 times higher. So Np upon Ns is equal to 4. So number of primary is 4 and Ns is equal to 4 Np. So this is 2000 turns. So 4 times more, because the voltage increasing 4 times. So number of turns on the secondary will be 4 times more than the primary. Exam style questions. Describe an experiment to demonstrate electromagnetic induction. Bar magnet and a coil, and here we have a bar magnet and a coil. This is coil and this is a sensitive galvanometer type instrument, and the meter shows the current is induced in the coil in one direction if the magnet is moved in, and in the opposite direction as it is moved out. When the conductor this is moved in, it shows the deflection, and when it moves out, it shows the deflection on the opposite direction. There is no deflection when the magnet is at rest. When the magnet is inside it and it stays there for longer duration, there is no magnetic deflection. It shows the deflection only when there is a relative motion. If the coil is moved here and there, then again the deflection will be shown here. The results are the same if the coil is moved instead of the magnet. Only a relative motion is needed. A relative motion between this bar and a coil is needed. Either a bar is moved inside the coil, or coil is moved toward the bar. This deflection will show. State the factor affecting the magnitude of an induced EMF. Faraday identifies 3 factors that affect the magnitude of induced EMF, and it can be shown here. The speed of the motion of the magnet bar. This magnet bar. Speed of the motion of the magnet bar. The number of turns on the coil. This number of turns on the coil, and the strength of the magnet. The strength of the magnet. How much field it carries. The strength of the magnet, the movement of the magnet or relative motion between the coil and the magnet, and the number of turns of the coil. So three factors: number of speed of the motion of the magnet or bar, relative motion, number of turns on the coil, and the strength of the magnet. So these three factors will increase the magnitude of the EMF. So magnitude of the EMF depends on these three main factors: speed of the motion of the relative motion of the magnet or coil, the number of turns on the coil, and strength of the magnet. The strength of the magnet, the relative motion between this coil and the bar, and the number of turns on the number of turns of the coil. Describe a deflection observed on the sensitive center 0 meter G when copper rod XY is connected to its terminal and is made to vibrate up and down as shown by the arrow between the poles of a U-shaped magnet at right angle to the magnetic field. So here we are moving up and down. This experiment indicates that an EMF is induced in the conductor where it is linked by varying magnetic field. So when we change this bar, we are actually forcing it up and down. We are creating motion, mechanical motion, up and down, and as a result the EMF may be induced when it linked by varying magnetic field or when it moves across the magnetic field. So as a result of this relative motion, a varying magnetic field appear across this bar, so EMF will be induced. Explain the behavior of the meter in a part A. The meter shows the current is induced in the coil in one direction as the magnet is moved in, and opposite direction as it is moved in and out. When it moves in, it shows the deflection in one direction, and when it moves out, its deflection will be on the opposite direction. There is no deflection when the bar is at, or this coil stays here for in a rest position. Then there will be no deflection or no EMF will be induced. EMF induced only with the relative motion, flux linkage, change of direction, relative change of flux, rate of change of flux. This EMF induced with the rate of change of flux. So explain the behavior of the meter in this. A simple AC generator is shown in figure. This is magnet, coil, slip rings with carbon brushes, and this is the terminal. Here A is slip rings where the carbon brushes resides, and the output is taken out from here. So B is showing the carbon brushes and A is the slip rings. The purpose of slip ring and carbon brushes, the end of the coils are joined to the slip rings on the axial, and against which the carbon brushes presses, and this carbon brushes, the output EMF is obtained from the output of the carbon brushes. This EMF is taken out from this carbon brushes and applied to the load. Describe change that could be made to increase the EMF generated. Faraday shows that observed that the speed of the motion of the magnetic coil, relative motion of the magnet or the coil, speed of motion of the magnet or coil, the number of turns on the coil, the number of turns increases. This single turn, if we increase it to multi turns, then definitely the EMF will increase. If we increase the strength of this magnet, or if we change the speed of the motion of this coil or turn. So these three factors are there: speed of motion of the coil or magnet, number of turns on the coil, and the strength of the magnet. Sketch the graph of EMF against time for the generator and relate the position of the generator coil to the peak, trough, and zeros of the EMF. So we have already discussed it. So this is basically the diagram. When it is in parallel, no EMF induced. When it's move up and down, the coil is vertical 90 degree is making 90 degree maximum EMF is induced. At this, again in parallel direction, no EMF. Parallel direction, no EMF. This direction, negative EMF is induced. Again. So sketch the magnetic field lines and around a current carrying solenoid. This is the current direction using a grip. The magnetic field lines will show this direction. Since it is in the clockwise direction, so north will be like this. From north, it exits from the north and collects at the south. The magnetic field of lines will be at here. North pole is here and south is here. Using a simple right hand grip rule, using a simple right hand grip rule, and this shows the current direction, this is north direction. Part of the electrical system of a car is shown here. Here we have a coil relay, and this relay basically start this motor. When we start the switch, connect a switch by a key inside the car, and this makes a circuit. So this voltage is applied to this coil, and as a result of this supply, this magnet will make this contact of the relay, and as a result of this contact, this power from this battery is applied to the starter motor. This starter motor will start or crank the engine. Once the engine is cranked, then the engine electrical system starts the car, and afterward this starter switch is disconnected and the contact is open. Now the engine has ignited and it works. So this relay helps to start the motor, and the motor start the engine of the car. Explain why connections are made to the car body for the neutral path to complete the loop. So this is a neutral path which is connected to the body. There are two circuits in parallel with the battery. One circuit is in the ignition coil. This is ignition coil, and while the other one is the starter motor. This is the starter motor. Through the contact, the starter switch energizes the coil of the relay, thereby they start the starter motor. As a result, the completing path through the relay contacts. Wire A is thicker than wire B. Wire A is thicker because it is in the power circuit. Wire B is just a coil supply, so this is a thinner one. This B wire contains a low current, so it is thinner, while A is a load motor, so this is a thicker wire. A relay is used to run the starter motor of a short while to crank the engine. The relay is used to start the starter motor which cranks the engine. Afterward, the relay contacts drops off. Explain how a loudspeaker works. Loudspeaker, we already discussed it. It works on the principle of electromagnetic induction. A varying electromagnetic field inside this voice coil varies. As a result, this pushes it up and up, back and forth, and as a result, this cone is vibrate. And in this way, electrical signal is converted into an audible voice signal. and it works on the principle of electromagnetic induction. Describe an experiment to show that a force acting on a current carrying conductor in a magnetic field, including the effect of reversing the current or the direction of the magnetic field. So the force increases, the strength of magnetic field increases, and the current increases. So simple. This is a demonstration setup. Here we have a conductor, and this is magnetic field, and we can change the direction. We can increase the magnetic field if we have an electromagnetic circuit, or with the speed of the motion of this coil. Using Fleming's left hand rule, we can the first finger points the field direction from north to south, while the current is coming out, so force will be upward. In this direction the current is coming out, so force will be in the upward direction. The current is going inside from here to here, the force will be downward. So secondly, if a current is carrying in a magnetic field, this is applied magnet, and a current is coming out. As a result, this another magnetic field, this current inside the coil is developed, and this will interact with this main magnetic field, and result the force in the wire will be appear like this. So this current inside the coil will develop a magnetic field around it, which will interact with this main field, and the combined effect will be appear like this, combining of both fields as shown in figure this. The current carrying coil experience a turning effect in a magnetic field. It states the effect on the magnitude of the turning effect of increasing the current in the coil. On increasing the current in the coil, the turning effect will increase. Reducing the number of turns in the coil, the turning effect will decrease. Increasing the strength of the magnetic field, on increasing the strength of the magnetic field, the turning effect will increase. Electric motor is used to raise a weight attached to a string. Select which of the following is used to transfer energy in the process. So in the electrical motor, the electrical motor works transfer electrical energy into mechanical form. Transfer the form of electrical energy into a mechanical energy. So electrical motor will draw more current to raise the load attached to its shaft via string, and this is electrical energy is used to do some mechanical work. So electrical working. Electric motor is used to raise a weight attached to a string. Select which of the following is used to transfer energy in this process. Electrical energy is transferred to a mechanical energy. So electrical working. Draw a labeled diagram of the essential component of a simple DC motor. So this is a simple DC motor. This is north magnet, south magnet, and this is a turning coil. And instead of a slip ring in like DC AC generator, unlike AC generator, we use a commutator or a split ring. Here we have insulators between this half ring. So as a result of this commutator, the DC voltage is obtained here. As a result of this split ring or commutator, the DC voltage is okay. So in a DC motor or DC machine, we have commutator or split ring which generates a DC voltage. Explain how a continuous rotation is produced in a DC motor and show by the direction of rotation is related to the direction of the current. So commutator basically, or commutator or split ring, basically this part will comes to this in a one turn, half turn, and after that this will appear. So as a result, this positive and negative effects changes, and it shows that the currents are in the same direction. Apparently it looked like. So state what would happen to the direction of the rotation of the motor you have described if the current direction was reversed. The motor direction will also change, reverse. The magnetic field was reversed, the motor direction will also reverse. Both current and fields were reversed simultaneously. If both are changed simultaneously, then the direction of motion will remain same. So if one of the direction is changed, then the direction of the motor direction will change. If the magnetic field change or reverse, the motor direction will change. If the magnetic current direction change, its direction will change. If both current and fields are changed simultaneously, the direction of the motion will remain same. Describe the construction of a simple transformer with a soft iron core. Here we have a transformer. Transform changes an alternating voltage from one voltage value to another, or greater or smaller value. So smaller, if we increase the voltage, we call it a step up transformer. If it decrease the voltage, we call it a step down transformer. So both primary and secondaries are turned on the same coil. Here we have a separate core here on this side and this side. So both type of transformers are used. If the number of turns are increasing on the secondary side, means voltage is increasing on the secondary side. If the number of turns on the secondary side is decreasing, means voltage is decreasing, and it is a step down transformer. So transformer equation is simply primary voltage, secondary voltage, primary turns, secondary turns. So primary voltage, secondary voltage, primary turns, secondary turns, and this is primary voltage, secondary voltage. Primary voltage is lower and secondary turns is higher. Primary turns, number of turns are lower. So this is a step up transformer. Primary voltage is higher, secondary is turns, primary turns is higher, primary voltage will be higher, secondary voltage is lower, secondary turns will be lower. This is a step down transformer. A step up transformer is used to obtain a potential difference of 720 volt from a main supply of 240 volt. So this is increasing 3 times. So calculate the number of turns that will needed on the secondary if there are 120 turns on the primary. So 740 volt, 240 volt to 720 volt. Primary is 240, secondary is 720. So number of turns on the primary is 120. So in place of this equation, number of turns is obtained 360, because stepping up. So primary is given as 120 turns. This is primary. The secondary will increase because the primary voltage is lower and the secondary voltage is higher. So the secondary turns will be 3 times, because the secondary voltage is 3 times increasing. So secondary turns should also be 3 times. So that is 360 turns. Explain what is meant by the following term in connection with the transformer. Primary alternating source is applied to the primary winding of the transformer. Secondary, as a result of the mutual induction, voltage is induced in the secondary winding. On the primary side of the transformer, we apply the voltage, and on the secondary we get the output. Step up transformer, the more number of turns on the secondary. Step down transformer, few number of turns on the secondary. Calculate the number of turns on the secondary of the step down transformer, which would enable a 12 volt lamp to be used with a 230 volt AC main power if there are 460 turns on the primary. So number of secondary has to calculate. Voltage on the secondary is 12 volt, primary is 230 volt, number of turns on the primary is 460 volt. the number of turns on the secondary will be much lower, because the voltage is on the secondary is lower, 12 volt, so the number of turns on the secondary will be much lower than this one, which is 24 turns here. Two coils of wire A and B are placed near to each other. Coil is connected to the switch and battery. Coil B is connected to a center reading B. So if the switch is connected to the coil are closed, this is closed a few seconds and then open, the meter reading on a coil B will be affected. When we close this switch, although this is a DC supply, but in this switching phenomena, a small, for a short while, this current will increase, and this number of turns will create a changing magnetic field. As a result, the effect will be appear here, and afterwards, when the switch is closed for longer duration, no EMF will be induced. And similarly, when open the switch, the same phenomena will appear with a negative or opposite direction deflection, nothing else. When we keep it closed or open for a longer duration, no EMF or no deflection will be appear. What changes would you expect if the bundle of the soft irons are placed through the center of the coil? Give reason of your answer. If the number of coils or bar is placed inside, the magnetic field strength will increase, the deflection will be higher in that case, or high voltage will be appear. Explain the use of transformer in the transmission of electrical power. The efficiency will increase because the transformer step up alternating potential difference ups and down accounts for use of AC rather than DC in a power transmission. So transformers are always used in an AC transmission system. High voltage are used in a transmission of electrical power so that a smaller current can be used to transfer the energy. If the voltage is increased, then current will reduce, and as a result, the lower conductor size will be used, and this transformer is used to step up the voltage for transmission of electrical power with a high efficiency. So voltage will be higher, more smaller current will required to flow through the secondary side, and the transmission will be easy, and a low conductor size will be required. Efficiency will be higher, and transmission losses will reduce significantly with the high voltage. This is one of the reasons we use the high voltage transmission system. Give two reasons for use of high voltage in a transmission system. Reducing the amount of the energy loss as a thermal energy in a transmission system, because due to high voltage, the current on the transmission side will be reduced, and I square R losses or current losses in the conductor will reduce, because the current is reduced due to high voltage on the secondary side. The current will reduce, and when current is reduced, I square R losses, thermal energy loss in the transmission will be reduced, and when current is reduced, the conductor cross-section area will also reduce, allowing wires with a small cross-sectional area with a high voltage. These are cheaper and easier to handle than a thicker wire required to carry large conductors. So smaller conductors will be required, and a smaller current will flow inside the transmission line. So smaller current will flow, as a result losses will reduce, one advantage. Second, the conductor size will decrease significantly, and it will be easy to carry. So these two advantages of AC voltage transmission of electricity is given here. That's all from this chapter.